So it's a pleasure to have Albrecht Klemm talking about the analytic structure of the all-loop banana amplitudes. Please go ahead.
Okay, thank you very much for having me in this conference. And this is a work which I have done in collaboration with all students from Bonn, which are indeed very good. And it is based on two papers, one that we released in December last year, and one which is very recent. And now I have to. So let me give you a short introduction. I fear that you know everything, and but we consider a Feynman representation of the graph contribution in terms of an integral over graph polynomials, and it is so that the graph polynomial in the numerator is actually independent of the physical parameter, which are the momenta and the masses. And then we have here this measure, which turns out to be a measure on Pn, and we have a region that I describe in a second. So moreover, D is the dimension, and N is the number of edges or propagators, and nu I is their multiplicities. And then we introduce a parameter omega, which is basically the sum over these multiplicities, minus L, which is the loop order, the number of loops. And of course, if the graph has an Euler number, then you can give the vertices in terms of the data that I have mentioned before. So let me come to this integration domain. It's basically, as I said, it's in Pn minus 1, and it's in homogeneous coordinates written here, and all the xi are positive real numbers. And that is a chain integral because we integrate over an open domain. But then on the other hand, the measure we know very well from Calabi-Yau period integrals. It is basically the standard measure on Pn minus 1. And so I only will calculate one graph, but of course, generically you need dimensional regularization, and you evaluate therefore in D minus 2 epsilon dimensions. And it is, so to say, well known by work of, very important work, that all this epsilon expansion will be twisted periods, or potentially actually general Calabi-Yau motifs, which are realizes minimally in L minus 1 dimensions. And I want to give now a very concrete example that has been featured, of course, before in the talks, namely a very simple series of such Feynman amplitudes in 2 dimensions. And this is, so to say, the Goldilocks case, because in 2 dimensions, the exponent of the graph polynomial in the numerator will be 0, and the one in the denominator will be 1. So in this case, we get a very fairly standard chain integral on a Calabi-Yau background that we can eventually discuss with methods that come from mirror symmetry. And that is more or less what I want to do. So, so this is this L-loop bananagram. You have just L plus 1 masses, and you have just one external momentum. And then, of course, this is a planar graph. And then, as I said, the exponents of the graph polynomials are so that you have only a polynomial in the denominator and this measure in the numerator. And it's convenient to sort of introduce dimensionless quantities. So you introduce a scale mu so that the t and the psi become dimensionless. And then you look careful at the numerator, and you see there a polynomial, Laurent polynomial. I mean, this piece is a Laurent polynomial. And this is what I call P delta L. And this Newton polytop of the Laurent polynomial is actually reflexive in the canonical rank L lattice. And here there are some figures for the first loops. So yeah, so this is for L equal 1 2 and 3. And you see, it's not so bad. They are all reflexive polyhedra. And that one is, for instance, the blow up of P2 in 3 points. And that is a K3 polyhedron. And some things look very good for mirror symmetry because we are used to the situation very much in work that we have done on Calabi-Yau manifolds. So basically, since this polyhedra is reflexive, there is a dual reflexive polyhedra. Both of them contain just one inner point, like this is the decisive feature here of this polyhedra. And then you can take a Calabi-Yau and the mirror Calabi-Yau as the section of the anticanonical bundle in the toric projective space, which is canonically defined by this reflexive polyhedra. This is, can be read in books of Cox and so on. And then we have Butterev mirror symmetry, and we get 2 manifolds, and the lower index always indicates the dimension of this manifold, so it's L-1, and they are both Calabi-Yau, and that is the mirror Calabi-Yau. So I use this joke that Candelas make, that W is mirror to M, and these are my 2 manifolds. And now you can look at the, one of these things is not work. Oops, I have a little bit problems with my keyboard. That is stupid. It is reacting slowly, but it's reacting. Okay, good. So, so the Feynman integral itself is, as I said, is a relative period or a chain integral over this real L-1 cycle that I have shown you. And, and given that fact, this is in principle straightforward to calculate this. And this was performed for L smaller than 3, also in the non-equal mass cases in 1, and for L equal 4 in 2. And so there are, from our point of view, various, straightforward steps. So you first determine the flat Gauss-Manning connection on ML-1, and then you solve for the periods where this gamma k is a basis of the middle cohomology of this manifold, and omega is the unique Calabi-Yau n form, or L-1 form in this case, which just exists on any Calabi-Yau space. So the first task is best done by starting with the Gelfand-Kapronoff-Selewinsky differential system, and then deriving the Picard-Fuchs differential D model from it. And what is a Picard-Fuchs differential D model? It's a complete system of linear differential operators that annihilate these periods, but they have no further solution. And it can be sort of, with a little work, it can be derived from it. And once you have this D model, you can, of course, easily calculate the Feynman graph everywhere in its moduli space. By this methods that we heard before, basically you expand the series and you design enough region of convergence, preferably near the singularities, and then you have an overlap region and you cover the whole physical moduli space. So if you solve this differential equation, of course, this leads first to the local Frobenius spaces, which I call warp psi hat. And this gives you a number of solution, which I call HL-1. And now you have to determine the linear combination, which correspond actually to the geometrical integrals, in particular to the Feynman integral. And you can also ask the question for the Calabi-Yau. Then you want to have the integrals which correspond to actually elements in the middle homology of the Calabi-Yau. And that can be actually easily achieved. I don't know whether you know that, but this is achieved by the gamma class formalism at the mum point. And I will use this also for the Feynman graph later. So then you commute the deformation modulus of the inner point. I mean, these are reflexive polyhedra and they have a unique inner point. So this ideal that you have defined before. And then you do this at the mum point. This is most convenient in special linear homogeneous coordinates, which are also fixed by mirror symmetry. And then you get the inhomogeneous equation that were also mentioned before. And we got them in the first work, well, in this form. And here there's where constant times logs maximally. But this is not a general feature. I mean, they still look simple, but there could be Z-dependent polynomials here and polynomials that depends on the log here. But you can determine, and we have determined this, for instance, for the for loop non-equal mass banana graph. It's not a big problem, so you can do that. So now you have this homogeneous solution to the system, which are in one-to-one correspondence to the periods on the Calabi-Yau, and they can be linear combined to get the maximal cut integral. And if you add the single inhomogeneous solution, you can write now the Feynman graph. So we have this basis here. This now runs from k equals 0 to L minus 1. So you get everywhere Frobenius spaces. And the Feynman graph will be a linear combination where these constants that I call lambda Lk are generic constants in C that you, for instance, can determine by this method of analytic continuation that we just heard. So that is, so to say, characterize the Feynman graph in all regions of the moduli space, and is a good way of solving these things. So for L equal 2, there were similar solutions found using Griffith's reduction method by Spencer Bloch and Matt Kerr and Pierre van Hove. But I have to say there are some shortcomings in this geometric description, and you can easily see that. I mean, if you think about this polyhedron, they were growing very fast is the dimension, in particular the vertices were growing very fast. So if you think a little bit about it, then you see that the dimension of the deformation space, which are, so to say, all the vertices at the edges of the polyhedron where I have to put small m values, which depend in some complicated way on the physical m's, this grows with L squared, and it grows, of course, much faster than the number of physical parameters, which in this case only grows with L plus 1. And if you think about the total cohomology of this space defined by this reflexive polyhedra, then you will find that the relevant periods are only a very tiny piece of the middle cohomology of this Calabi-Yau manifold. And therefore, the derivation of the physical relevant periods becomes more and more cumbersome. And another problem that I want to solve in this talk is that these coefficients could be only determined approximately by a numerical analytic continuation. But in this talk, we will do much better. So to overcome these problems that I mentioned, we propose a better Calabi-Yau motif for the banana graph and new gamma hat classes. And these are inspired from homological mirror symmetry and will solve the problem very, very beautifully, I think. So what is the better Calabi-Yau motif? Well, I mean, if you look at the Feynman graph, then you look at the mirror of the Feynman graph. This I call WL minus 1. And this is embedded in the Fano variety. And what I want to propose is basically a Calabi-Yau, which is written in this form. So what is it? It is a bunch of P1s, actually a product of L plus 1 P1s. And in this P1s, you have one hypersurface constraint, which is of degree 1 in every coordinate of the P1. And then a second one, which is also of degree 1 in every coordinate of the P1. And by the adjunction formula, I will easily see that it's a Calabi-Yau. And moreover, it is embedded into a Fano variety, which has positive Chern class, which is obtained by just leaving away one of these constraints. And this I will call in the talk FL. So this WL are complete intersection Calabi-Yaus, as we call them, and the way that they are described, I have just explained you, just that I want to say this complete ambient space, which is this product of P1s, I call AL plus 1. And that is also the ambient space of the Fano variety, which is the degree 1 constraint in this space. So then there is some amazing beauty to this picture, because you see every mass corresponds precisely to one of these rational curves in this Calabi-Yau. And if you start thinking about it, then you realize there is a very nice relation between the volumes, or we in mirror symmetry say quantum volumes for a reason that become clear immediately, with the masses of this Feynman graph. So it is that you have all this L+1 rational curves, which are actually visible as P1s. And their quantum volume, what is it? So you take the symplectic form, which any Calabi-Yau is scalar, so you have symplectic form. And in mirror symmetry, we make this complex, so we add the B field. But actually, this real part of this, note there is a 2 pi I here, is simply the area of this P1. And the area of this P1 is just the logarithm of the mass squared over the momentum squared. And we will introduce canonical coordinates for that, which are called ZK. And now this is a good picture at this high energy, super high energy region of this Feynman graph. And this thing becomes 0, and then the logs become, and then these area become infinite infinite. And away from this area, there are quantum correction, which we call instanton correction, and they are going with e to the exponential of this volume. So they are suppressed in this limit. But nevertheless, you can actually calculate them, and that was done in a paper by with Yao, Tyson, and Hosono a couple of years ago, actually. And this has a very easy GKC system, much easier than the GKC system of the reflexive polyedra. And if you solve this GKC system, of course, you get all these exponentially suppressed terms, and you get the full Feynman graph integrals. And also now we have no redundant parameters as we had before. We have just the parameters which corresponds to the volumes of this P1. And in mirror, after mirror duality, I call them ZK. So K really runs just from 1 to L+1. And then there is a very nice vibration structure in this whole picture, because think what is the elliptic curve? So the elliptic curve is, of course, one complex dimensional. So you take a 3 complex dimensional space, which is 3 P1s, and you put 2 hypersurface, then you get the elliptic curve. It's, of course, again, a Calabi-Yau, so it's an elliptic curve. And that is associated to the 2-loop graph. And then the K3, which is associated to the 3-loop graph, is now fibered in 4 ways by this elliptic curve, because over every P1 that you can put here, you have this figure here. And of course, it doesn't matter which curve you put. You get a K3, which is in 3 ways fibered by an elliptic curve. That means you have for this K3, 3 contractions to a P1 in 4 different ways. So 4 contractions. And if you go on, then you see that the Calabi-Yau threefold is now fibered in 5 ways over the P1s. I mean, so the Calabi-Yau threefold has 5 K3 vibration structures. Each of these K3 has 4 elliptic vibration structures, and so on. So this looks like a very complicated vibration structure. But it just reflects the fact that you can send the masses in arbitrary order to infinity and obtain a lower loop graph. And the lower loop graph is obtained by the lower dimensional Calabi-Yau. And of course, since the masses are the volume of the bases, you see that this corresponds to this vibration. So in this limits, the base decompactifies, and this basically exponentially suppresses the corresponding instantons. And also, if you say that the full graph, as I will argue then in a second, is described by a general GKC system, you can get in many, many ways to your favorite elliptic logarithm or whatever in every fiber. So we can also see that the intersection calculation done for this gamma class, we have to do them anyway, reveals that this Oguisu criterion for the vibration structure of Calabi-Yau is fulfilled. So now let me get, so to say, a first view on the analytic structure that I really want to discuss. So we have here the equal mass case for simplicity, but in fact, it will not make a big difference at the end because we can also calculate this analytic continuation constants for the non-equal mass case, as you will see in a second. So what is this moduli space? The moduli space for the one parameter Calabi-Yau is just a P1, and there are a couple of points missing. And these points we have seen before. For instance, there was this 25 for the for loop graph, and then there was this 9 and so on. These are the lower order singularities, but it is like this, that there are two very important points. This is this point of maximal unipotent monodromy, where, as I said, the volumes of all the P1s are infinite. And then there's the point S equal infinity, where people have over many years worked out a very beautiful description of this Feynman graph in terms of Bessel function. And then for the actual integral that I was considering, of course, you can consider also other period integrals, then this conifolds will be also of relevance. But for the actual periods, for the actual integral I'm considering, the radius of convergence is limited by this last conifold point. And then there are, so to say, less important points. I would say there is a point where this thing becomes pure torsion. Then you can actually express even the Feynman graph in this. The Feynman graph becomes pure torsion in the homology of the Calabi-Yau, and then you can get some special values for this fiber. And then there are also the fibers where S is an algebraic numbers. This were found by Candelas recently, and there the Hasse-Weil zeta function splits, and you can make also some exact calculations. So as I said, to simplify the presentation, I restricted to the equal mass cases, but later on we will see that there are many things that I can see also about the general case, So, so this diagonal differential D model, I mean, it's just one operator, has order L. So for instance, for the for loop graph, it would be this differential operator. And here from the symbol of this differential operator, you see again the conifolds discriminants. And this is just an example. And then the inhomogeneous term is, so to say, universally given by L plus 1 factorial. In this case, it's 120 factorial. So let me, so to say, now go to the important singular points. So there is this Bessel points, and over the years, the people have expressed the amplitude in terms of a Bessel function integral. So you cannot express it exactly as a series, but you can do a very good thing. I mean, you can sort of say express it in terms of a single integral over a bunch of Bessel functions. And these Bessel functions contain T, which is 1 over S, and they contain also this dimensionless mass parameter. But as I said, the radius of convergence of this expression is limited by the last conifold. And in general, it would be limited by this divisor here where the masses go in. And it's also very simple to get this DL because you take just the symmetric product, the L symmetric product of this Bessel function operator, which is trivial, and then you take 2 times the Borel transformation, then you get this operator that I have showed you here. So that's a general feature. And now let me talk about the conifold. So at the conifold, in our case, this is only singular at this last conifold, which is at S equal 1 over L squared. And what happens here, there is a single cycle in the middle cohomology of my Calabi-Yau, which vanishes. And according to Lefschetz, that gives rise to a reflection monodromy if L is odd, which is really a square root cut, or a logarithmic cut, which is called a symplectic reflection in the speech of these people, or a shift if L is E. So now by homological mirror symmetry, I can actually, I will be actually able to determine the homology of this vanishing cycle exactly in terms of the gamma class of the structure sheaf on BW. And you will see this is very completely explicit in terms of beautiful zeta functions and so on. And this fixes actually the Frobenius constant exactly, which in turn specify the conifold monodromy in this Frobenius spaces. And, in the path of the analytic continuation that we chosen here, this conifold cycle will actually be exactly the imaginary part of the Feynman amplitude once you go around this conifold. So, so then there is another very interesting point, as I mentioned. I mean, there was the Bessel function, the conifold. Then there's this point of maximal unipotent monodromy, and that is S equals 0. So that is, you can also say what it is in general. It's not very complicated. In general, it's a normal crossing point of divisors, which are given by these masses. And it's also a point. It's not a divisor because these L-1 divisors meet here, and then in the L+1 dimensional moduli space, it's a point. And what happens here, the monodromy matrices MI, so why it's called maximal unipotent, they fulfill an equation when you take this monodromy and subtract 1 and take it to the power L+1, then it's 0. But what means maximal is that it doesn't happen for any lower power for all the matrices. That is what maximal unipotent means. And according to Wilfried Schmidt, this maximal unipotent behavior is caused by a hierarchical structure of degenerating cycle. So there will be logs and higher logs and so on, and they correspond to degenerating cycles. And that's exactly what happens here. And at the mirror dual point in the complexified Kähler moduli space, I call this complexified because we had the Kähler form, we integrated to get the volume of the curve, but then we had this B field. All the rational curves are big. And in this resulting classical geometry, we formulate a new gamma class conjecture for the Fano ambient space, which exactly captures now also the real part of the Fano space. So let me give a couple of small comments about these fibers with special evaluations. So there are fibers where the cohomology of the Calabi-Yau does something special, as I said already, as S equal 1. Then the Feynman graph is pure torsion in the cohomology, and you can actually make beautiful, find beautiful values for that. And that has been done, I think, for up to L equals 6 or so. These are usually L function values of Hecke eigenforms of a certain of weight L. And then there are these rank 2 attractor points. They exist, so to say, we don't know, but they exist according to the analysis of Candelas only for L equal 4. And here, what happens is that the Hasse-Weil zeta function of the Calabi-Yau factorizes. So it factorizes into 2 terms, and you see this coefficients AB. And here you see, of course, this is just the Hasse-Weil zeta function of an elliptic curve, and this is the Hasse-Weil zeta function which gives weight 4 modular form. And you can find these modular forms easily. I mean, basically, there is a method, periodic analysis of the periods. And this PP are Fourier coefficients of a weight 4 and weight 2. This is for the elliptic curve, of course, and weight 4 Hecke eigenform, which is given here. And that was found by Candelas, Elmy, van Straten. And then you can actually calculate the periods and the quasi-periods of these forms. That's not difficult. It actually be done in the master thesis of my student, and apparently also independent by Broadhurst, which in addition had a very nice feature that he also, I mean, that would determine all the periods for the maximal cut integral, but he had also, as I saw yesterday, a very nice method to get the full Feynman. But anyway, the master thesis of Kilian is super good and is also worth to be cited. So let me focus on the points which are really important, which are really singular. So now we follow this paper that I mentioned at the beginning that we wrote in '93, and we construct the Frobenius solution at this MUM point. And there is, so to say, a technical tool which is called the Frobenius cone, which is dual to the Kähler cone. And I should have stressed one thing very much. I mean, what I want to calculate is the vertical cohomology of this Calabi-Yau. I have stressed it in my slide, but not in saying. So we want to calculate the vertical cohomology of the Calabi-Yau. That is the one which is so small. And that is the one which is good. And that is the Calabi-Yau motif we are after. So this vertical cohomology is, of course, just, I mean, at lowest dimension is based on this P1s that you see in the Calabi-Yau. And the Mori cone will be L+1 Mori cones, and they represent these curves. I mean, this P1s. And this Mori cone is given by this expression here. So it's here is -1, -1. This basically comes from the constraint. And then there are 2 1s which wander out until they are here, until when you have L+1. And then from that, you obtain a generalized Gelfand-Kapranov-Selewinsky system that we already did in this paper with Yau. And, and using the Frobenius deformation method, or now is sometimes called in this context Giventhal's I function, because he has proved it on the mirror side, we can write down this expression here. And this expression, you see, has a deformation parameter, which I call epsilon, or rather L+1 deformation parameters, which I call epsilon underlined. Here should be also underlined. And from that, you can get all the solutions. So basically, you realize that these Mori cone generators give you certain factorials, because this is a generalized hypergeometric function. So you see something like Pochhammer symbols, and they are given here. And then the epsilon deformation is done as usual. You just promote all the factorials to gamma function, and you deform all the generally all integers to epsilon+1, and therefore you get this also like here. And then you can immediately get all solution by just taking derivative with respect to epsilon. But let me first say what is the at the point of maximal unipotent monodromy, there is a unique holomorphic solution that's given just by taking no derivatives, just by setting epsilon to 0, and that is written down here. And this set K is just this S parameter times this dimensional mass. And then, as I said, all the other elements of the Frobenius spaces can be taken just by taking derivatives. But you have, of course, you cannot take infinitely many derivatives, because this solution system is finite. It's like the primitive cohomology of this Calabi-Yau. And which precise combination will lead to a solution is actually determined by the intersection number, or by the showering of the intersection number in the primitive cohomology of W. And it's very concrete. You can basically immediately construct all the solutions at this point. And what is very important here, the dimension of the primitive cohomology, vertical cohomology of VW maps to the primitive middle horizontal homology of the mirror. And these are the ones which determine the solutions, these K-order logarithmic solution. And what is, of course, nice is that this primitive cohomology doesn't grow so much. So when you ask yourself how many logarithmic solution with log to the K I get, you just look here and that's what you get. So this is the number of the primitive cohomology, and this is also the number of solutions that you expect in each log order. So now I have described how you get the basis. It's straightforward. You can do it to very high precision, of course. They converge very nice until this next conifold. And now the statement is that this banana diagram is a linear combination of these Frobenius spaces. And I have to know which, because otherwise I cannot do too much. And now we have a statement, which, so to say, in the paper we have just formulated that statement, but since Monday, I have received many mails from Iritani, which is a world expert on these gamma classes, and I think is now more or less a theory. So the point is that these lambdas that I have here, which are, so to say, tell me of how I express my basis for the actual Feynman graph in this Frobenius spaces that I can quickly construct, is that this lambda are given by the following generating series. So it's basically that lambda L is x to the L. I mean, this is a generating series, and here you expand the gamma functions, and this is the Euler-Maccheroni constant. This is called, so to say, the regularized gamma function, because you don't want to see all these Euler-Maccheroni constants. And then you expand it, and that gives you these coefficients with which are coming with the holomorphic solution. Then you ask yourself what comes with the first logarithmic, the second logarithmic, and the third logarithmic. And the answer is again very simple in the theorem. It's just given in the following way. And then the vanishing cycle at the conifold, which is so to say the integral over an S3. So nu has topology of an S3 and gives this a square root cut in the even case and the shift log in the odd case. This is given just by the imaginary part of these lambdas, so generated. So it's also completely fixed. What is the vanishing cycle at this point? So let me give you an example that you can see. I mean, now we have, so to say, we have this omega. So this goes without any log. This goes with a single log. This goes with a double log. This goes with a triple log. This goes with a quadruple log. And you ask yourself, what linear combination do I have to take in a certain normalization that you have to specify a little bit more carefully? You can read this in the paper. I mean, you have to set certain things to 1. And so what you get is exactly this coefficient. So you have, for instance, for the 5-loop graph, you have to take minus 288 sigma 5 plus 144 sigma 2. I also put the pi into sigma because it reads nicer. And then sigma 3 and so on and so forth. And if you want to have the leading logs of the Feynman graph in the high energy expansion, you just look at this. So this is true for all loops. So you can do this for actually, I mean, we have checked this because once you have, you know the form, you can check this to hundreds or even thousands digits that is true. And we check this up to loop order 14. It's always the right, I mean, this is just the right expression, and it has to be the right expression because I claim I can prove it. So now the idea to prove this theorem or whatever it is uses this gamma class, and it provides also an immediate generalization for the L-loop banana graph with arbitrary masses. So let's take, then you have a second index. So basically this counts the number of loops, and this counts the number of elements that have that many loops. And the number of elements that have that many roots is logs is just given by the primitive cohomology of L minus 1, which of course I have already given. And now this linear combination look a little bit more complicated. You have now here this number of solution which correspond to the primitive cohomology of BW minus L, and you have to find all these L's. And I can tell you that I can find this else just the same way. You will see if I turn to the proof of this statement. And then you see, okay, I mean, for 4 loops, you get the same, of course, the mixture to the Feynman graph of the unique holomorphic solution is still given like that. But then the others, they split. And why they split so symmetric? Because this thing is so symmetrically fibered. So when you put various of these t's to infinity, you get the same subleading Calabi-Yau, and the coefficients can be also calculated. So let me come to the idea of the proof using this gamma class. So essentially, it's a calculation in the vertical homology of VW and the Fano variety FL, I should have written. So like here. This is just the dimension of these guys. So basically, we guessed first, I mean, the complicated part was to guess the Fano variety, the gamma class for the Fano variety. And I first guessed it. And then, as I said, Iritani got very excited and wrote many mails and said, this is the right thing to do. And I will tell you what is the right thing to do. So basically what you have is now you take the mirror map, and the mirror map is basically just a single logarithmic solution divided by the holomorphic solution. And that is precisely what gives you the quantum volume of each of these P1s. And then you take the symplectic form. I mean, this is maybe hard to distinguish from this W, but you take the symplectic form either of the manifold or the Fano. I mean, either of the Calabi-Yau or the Fano. I call it in the same way because not to clutter the notation, but they are both, of course, scalar manifolds. So you have to certainly have a symplectic form. And then you expand, then you define for a rank S, a rank N sheaf S, you define the regularized gamma class. I mean, this was done first by Kazakov, Kontsevich, and Pantev, and then later Iritani, Goldachev, and Galkin. And even in our paper with Yao, we had already some ideas how this derivatives with respect to gamma give actually rise to these coefficients. So, so then, according to Seidel, he tells you that this vanishing cycle of the conifold is just this gamma class integrated over the Calabi-Yau. Okay, so that's what it is. So then the other thing, and that's, as I said, we first have guessed it, but then Iritani has said it's not in the literature, but it's not close to something that he can prove. That is this one. So, so then when you know that, then the rest of the thing is just standard intersection calculus on this Calabi-Yau VW -1, which, or FL of the Fano variety, and that's really, really easy. So you have the adjunction formula. So you have basically the tangent bundle and the normal bundle, and the normal bundle is squared because you have two constraints of 1, 1, 1, 1, 1, and then you take the degree k coefficients of this expansion, and then you get the Chern class of VW. So that's easy enough. And then, of course, the hyperplane class in each of these P1s fulfills H2 equals 0 because two hyperplanes in P1 don't intersect anymore. There's no space for it. And then you can express the Chern class in, because of this fact, there will be never higher powers of H. Then you can basically express the Chern class in terms of elementary polynomial Sk in this form. And you find a certain normalization factor, which I call NWL. And then similar, as you have the adjunction formula, but you want the Fano variety, you leave away this 2 and do the same thing. And then you get the Chern classes of the Fano variety, and they are written there. They are also given in terms of symmetric polynomials. And then you notice, I mean, with a little calculation, that if you evaluate the Chern class, the highest, you have, of course, to take the highest combination of Chern classes, which gives the dimension of this space. Then it's given by these normalizations that I given before. I mean, they are different for the Fano and the Calabi-Yau. That's why I've just put here an X. And so you can calculate these Chern classes. And then, of course, you have also very simple coefficients of the intersection rings. I mentioned before, they match with the criterion of Oguisu to have a vibration. They are also just linear in the hyperplane classes. And that is true for the Fano variety as well as for the Calabi-Yau, only that here this is of course one class more, and here is a 2. And now you get simply the theorem by evaluating nu t and the Feynman graph in finite power series of t. So you take this expression here, for instance, and there is a t, and this t evaluates, and when you bring down the W, you can integrate it, and if you expand this in symmetric powers of the Chern classes, this expression, you get, for each t power, you get a coefficient, and this coefficient is the coefficient I showed you in this table, and the coefficient is the one that makes this formula exactly the generating function of all the connection matrices that you get. So in this way, you know now that you can actually calculate this connection matrix exactly. So it's not a numerical value, it's a certain combination of set values. So, so this was the proof of these two theorems, which basically give you all the connection. I mean, you know the Feynman graph, let's say, in the up to this way just of conversion, and beyond that, this is the complete answer for all L. And so to say, let me come now to the conclusions. So the solution of this Goldilocks amplitude, I would say, is not very hard, as it's an amplitude which is much too easy, but it has probably and hopefully revealed some general feature that could pave the way for further progress in higher loop calculation in more complicated situations. So let me say some of the features that I see as being relevant. So one thing, what you should sort of say, taking more into account is this point of maximal unipotent monodromy. That's actually predicted by mirror symmetry for all Calabi-Yau motifs. And that fits perfectly with the high energy degeneration of the Feynman amplitudes. So if you study the high energy degeneration of the Feynman amplitudes with the gamma class formalism, you get the topological information about the Calabi-Yau, because all the intersection numbers can be actually recovered from that. And then, for instance, for the threefolds, we have nice classification theorems, for instance, by C.T.C. Wall, who says, if I know the intersection ring, if I know the evaluation of the Chern classes, the Hodge numbers, then I know what is the topological type of this Calabi-Yau. So this is basically the Feynman graph will sort of, you get him when you put them in this degeneration, it will tell you what topological type of Calabi-Yau you need. And also this, what is nice about this gamma formalism is that it explains some of this transcendentality structure, because after all, you're just expanding a gamma function, and that's why you get all this zeta structure. And maybe if you sort of do the master integrals, you can also get higher multiple zeta functions. But from this, for this integral, you never get higher multiple zeta functions, because it's just that you expand gamma functions. What we also see is, and that was also a little bit in this work of Kilian, he already know that what are the full period matrix. So we see that these banana amplitudes are also Goldilocks case for starting master integrals. And again, I think this degeneration will tell us a lot about them. And then another thing which I sort of realized by doing this with the student is that this rich databases of Calabi-Yau manifolds and motifs, for instance, provided by people by Kreutzer and Skarke, they have done a list of all the reflexive polyhedra in up to 4 dimensions. Then Almquist, Enkford, and van Straten, that's why this Calabi-Yau operator for L = 4 was, for instance, the ASZE operator 34, because they have a list of those. And you can find them there. That is at this page in Mainz. And then there is also a very important list about finding these holomorphic solutions for the Fano varieties that we also used. They can be found at this web page of codes called Fano Search. I mean, I wish this thing had a little bit more inverse searching, but they are with a couple of more features, they can become like the integrable tables of the future, at least as the one that extend elliptic integrals to Calabi-Yau integrals. And they can be extremely useful. And then if you combine this with the Skelpan-Kropanov-Sedovitsky system, you basically can provide super fast and super precise numerical evaluation. So for instance, if you don't know all these zeta values, then of course you are basically in the woods. You need a lot of time to see what combination of zeta values there are. But if you know the zeta values, you can easily check up to 1,000 digits that this is the right amplitude which matches, for instance, in a certain region, the Bessel function, or let's say at this region of attractor point, this periods and quasi-periods. And finally, on a more speculative basis, of course, I'm coming from topological string theory. We actually are not happy with just doing the genus 0 chromophitten invariants, which correspond to the periods, but we want to do higher loop amplitudes in the sense of worldsheet. So we have, I mean, it is true by the gist of mirror symmetry that these periods encode the rational curves on this Calabi-Yaus. But there is a very similar epsilon expansion, and this epsilon expansion, there is a refined version, and in particular in the Nekrasov-Saakashvili limit, there is something which is called exactly the epsilon. And I suspect that these higher terms are related by, like in these quantum periods, by differential recursion relations to each other. And this is, so to say, what exactly happens in the Nekrasov-Saakashvili limit, and which is an integrable system, and that probably could provide a deeper link of this expansion to integrable system. So I think that's all for now.
Thank you. And let's again take a couple of seconds to unmute ourselves. And I see David has a question.
Yes, thank you for this delightful overview. I agree entirely. We as high energy physicists can calculate the high energy, the massless limit, with great ease. We know we will only see from Banana diagram gamma functions on their products, and we can generate for you with great ease that matrix that you showed. I want to emphasize.
Can you sort of prove it in a sense that?
Yes, because the massless diagram is just given in-dimensional regularization by beta functions. And their expansions in epsilon essentially count logarithms, and the logarithms correspond to successive cuts of the diagram. So that was a back of the envelope calculation for me to find the linear combination of my amplitudes that corresponded to Philip and Xenia's Calabi-Yau solutions.
This general solution with the gamma classes, you also would know that, or I mean, it could be. I mean, this general generating function that that you get here.
I have to. I always work case by case, I'm afraid, right? All I can say.
But I mean, so to say, the beauty of having this series of all Calabi-Yaus is you can make really, and that's why I call it analytic structure of the banana graphs. You can basically make proofs for everything, and you don't have to calculate anymore.
Well, when you say you don't have to calculate, I mean, we're interested in numbers, right?
Well, at the end, you expand this thing and you get this expression. So you can do this for all loops. And also it's nice that you can do it, of course, for the massless case. It's just this. For the massive case.
But I have a very important question, an absolutely burning question that comes from your talk.
Yes.
It concerns the difference between the modular behavior where the Hasse-Weil zeta function splits at the singular point,
right,
x equals 1, and this wonderful splitting which Philip and Xenia and Duco and Elmi found at a regular point.
Right.
Now, the crucial thing from my talk is that the Feynman diagram itself, when you don't cut any of the lines, is not a Calabi-Yau period. The Calabi-Yau period.
I understand that. So
whereas at the singular point, and the magnetic moment of the electron, it is. So the actual thing that we calculate for the magnetic moment of the electron is the diagram cutting no things, and that is the period of the given by a period of the weight for level 6 modular form.
You mean at this point s equal 1, or?
Yes.
Yes.
The diagram itself.
No, I know. This is.
Whereas everything in my talk, right, at the other modular points at level 14 and level 34, those were just the solutions to the Feynman solutions. Combinations of the Calabi-Yau solutions. So my big question to you is, what is the thing which is not the Calabi-Yau period, the actual value of that diagram itself?
Well, I thought you had found it, but maybe I'm wrong, because didn't you found, so to say, I mean, I thought you claimed you found actually at this point the Feynman graph value, or not?
Yeah. No, it's the difference between when you cut one line, when you put one of the lines on its mass shell, then you get a solution to the inhomogeneous equation. That inhomogeneous term, 120 factorial 5 on my slide, which was on yours, right, refers to the actual diagram before you take any cuts of it.
Sure.
And everything that Philip and Xenia did, right, was for the solutions to the homogeneous equation. So
no, I agree completely. But let me tell you one thing. I mean, it's not true that this will be, that you get exact values only if the Hasse-Weil zeta function factorized. So basically, the Weil conjecture would say that for general point, I mean, for general rational points, or maybe rational points with extension, you find Hecke eigenforms of paramodular forms, Siegel paramodular forms. So this is just a tiny example that you get, so to say, by luck, that the Hasse-Weil zeta function calculates and you factorize, and you can do the calculation. But in general, the Weil conjecture tell you there is a Siegel modular form that gives you these values, exact values at all, at rational points. All right.
Yeah, but to come to these very specific cases, I would like to know, I really would like to know, because I can give you 10,000 digits of it, what in a mathematical context the solution to the inhomogeneous equation is at the modular points with level 14 and 34.
Right. Let me say, I mean, I mean, first of all, of course, this thing is not proven, right? I mean, basically, that Kilian was doing also, and he found actually many more rank 2 attractor points in other Calabi-Yau manifolds. So you can check with high precision that they are equal, but it's not a proof. And what you have to do the proof maybe provides the answer to your question. So what you have to do the proof is you have to construct the Kuga-Sato variety of this special fiber. And this Kuga-Sato variety might give you the answer what this additional period does. But let me ask you, because I had no time for your talk yesterday, and I also have to go to a thesis defense after my talk. But maybe we can talk later.
Yes.
I mean, that would be great.
We talk later. Thank you.
So is it true that you can determine the Feynman graph exactly or not?
The periods and the quasi-periods of the weight 2 and weight 4 modular forms, which are on my slides, which are already on this down there, relate to the Feynman diagram in which I put one of the internal propagators on it.
That is actually more or less.
And then I get the solutions to the homogeneous equation without
Right,
the factorial 5 down there. And I'm asking you, what is the real Feynman diagram at this modular point?
Yeah,
because
we looked.
Point, it is the period of the modular form, but it's not. Anyway, we should continue.
We looked at that and we didn't find it. So I thought you found it, but now as you're saying you don't.
No. I'll send you a more detailed version of my of my findings. But
okay, very
good. We're taking up too much time.
Yeah, thank you.
Matthias, you're muted.
Thank you. Are there any further questions? I do have a question myself. If I understand it correctly, one crucial point to go from your first paper to your second paper was that you found this realization where you had a much smaller moduli space. So is this just some coincidence that it is possible in this case, or is that something completely algorithmic that you can also do in any other case?
It's a contrary of algorithmic. So basically, we talked with Matt Kerr, and Matt Kerr looked at this database here. And that's why I think these databases are very important. And he made the observation that the holomorphic period is just for, I mean, if you click at this database, you find, you can put in the coefficients of the holomorphic solution, or maybe you can put in the form of the holomorphic solution, then you find this other motive. And then, of course, it is just like a charm. Then everything can be expressed in terms of this simpler motive, and all this these general formulas that I can give for the coefficients, for the transition coefficients, they are just coming like nothing. I mean, just because the cohomology of this other example is so much simpler than the original one. So that's why I'm stressing these databases. I mean, you have to, I mean, okay, I mean, maybe I'm stupid. I could have gotten to the solution, but if you have, let's say, I mean, one of the lessons that I have to say is important. If you have one holomorphic solutions, start thinking in which motives this holomorphic solution does appear. And then you find probably better motives, and that will lead you to more. And the other lecture is, the other lesson that I sort of was getting is that look at the maximal degeneration. It will tell you the topology of the geometry. I mean, that was also what David was saying. I mean, this is very simple. You know that that there is a very physical degeneration, and it's simple, relatively simple to handle. Take this one, engineer backwards over the gamma class. What is the geometry, and you get the rest.
Thank you. Okay, if there's no further questions, thanks again. And yeah, we'll reconvene in a bit more than 20 minutes for the next and last session of talks. And feel free to stick around or take a coffee and chat, and also now use the chance if you have any further burning questions for either Albrecht or for Martijn.
I have to